Table 220.54 provides demand factors for electric clothes dryers based on the number of units in an apartment complex. For 5 units, the demand factor is 0.80, that is, 80%. Article 220.61b states that where the maximum demand for a group of clothes dryers is calculated according to Table 220.54, the neutral conductor shall be sized to carry 0.7 times the maximum demand load. To calculate the neutral conductor size for the 5 electric dryers, firstly determine the maximum demand load for the dryers. The maximum demand load equals the number of units multiplied by the demand factor multiplied by the rated load per dryer. The maximum demand load equals 5 units times 0.80 times 5 kilowatts, which is a typical rated load. The maximum demand load equals 20 kilowatts. Secondly, size the neutral conductor to carry 0.7 times the maximum demand load. The neutral conductor size equals 0.7 times the maximum demand load. The neutral conductor size equals 0.7 times 20 kilowatts equals 14 kilowatts. Based on the calculations above, the recommended neutral conductor size for the 5 electric dryers in the apartment complex is 14 kilowatts. It is important to remember that the neutral conductor size must be compared to the ampacity requirements of the overcurrent protection device supplying the dryers. The neutral conductor must be insulated and color-coded white or gray. Neutral conductors must be sized in accordance with the National Electrical Code, NEC, and any applicable local codes. Let's delve deeper into understanding the neutral conductor calculations for electric dryers in apartment complexes, specifically focusing on the application of the National Electrical Code, NEC, sections 220.54 and 220.61b. These sections are crucial for ensuring the safety and efficiency of electrical systems in multi-unit dwellings. Firstly, we need to establish the context. We are dealing with an apartment complex that houses 5 individual units, each equipped with an electric clothes dryer. Our primary goal is to determine the appropriate size of the neutral conductor that will serve these dryers. This is not as simple as adding up the total nameplate ratings of all the dryers, because the NEC recognizes that not all dryers will operate simultaneously at their maximum load. This is where demand factors come into play. Secondly, let's discuss Table 220.54. This table in the NEC provides demand factors specifically for electric clothes dryers and dwelling units. These factors are based on statistical data that accounts for the diversity of dryer usage. For our scenario, where we have 5 dryers, Table 220.54 assigns a demand factor of 0.80, or 80%. This means that we can expect the total demand from the dryers to be only 80% of their combined nameplate ratings. The demand factor acknowledges that it's unlikely all dryers will be running at full capacity concurrently. Thirdly, let's consider a typical dry rating. For the purpose of this calculation, we'll assume each dryer has a rated load of 5 kilowatts. This is a common value, but it's important to verify the actual nameplate rating of the dryers in question for a more accurate assessment. It's important to note that dryer ratings can vary. Fourthly, we calculate the maximum demand load. To determine the maximum demand load, we use the following formula: maximum demand load equals the number of units multiplied by the demand factor multiplied by the rated load per dryer. Plugging in our values, we get maximum demand load equals 5 units multiplied by 0.80 multiplied by 5 kilowatts, which equals 20 kilowatts. This 20 kilowatt figure represents the maximum load we anticipate the dryers will draw at any given time, considering the diversity of their usage. Fifthly, let's address Article 220.61b. This section of the NEC specifically addresses the sizing of neutral conductors for electric dryers when the load is calculated using Table 220.54. It states that the neutral conductor can be sized to carry only 70% of the maximum demand load calculated. This is a significant reduction and reflects the characteristics of dryer loads. Electric dryers primarily use 240 volts for the heating element, which doesn't contribute to neutral current. The neutral current is mainly due to the 120 volt components like the motor and controls. Sixthly, we calculate the neutral conductor size. Applying Article 220.61b, we calculate the neutral conductor size as follows. Neutral conductor size equals 0.7 times the maximum demand load. Substituting our value, we get neutral conductor size equals 0.7 times 20 kilowatts, which equals 14 kilowatts. Therefore, based on these calculations, the recommended size for the neutral conductor serving the 5 electric dryers is 14 kilowatts. Now let's convert kilowatts to amps to help with conductor selection. To convert kilowatts to amps, we need to consider the voltage. Since we are dealing with a 240 volt system for the dryers, we will use that voltage. However, the neutral current is primarily due to the 120 volt components. We'll need to consider both. Firstly, convert the total demand load to amps at 240 volts. Total demand load is 20 kilowatts, which is 20,000 watts. Amps equals watts divided by volts. So amps equals 20,000 watts divided by 240 volts, which equals approximately 83.33 amps. Secondly, convert the neutral load to amps at 120 volts. Neutral load is 14 kilowatts, which is 14,000 watts. Amps equals watts divided by volts. So amps equals 14,000 watts divided by 120 volts, which equals approximately 116.67 amps. This calculation is crucial for selecting the appropriate wire size for the neutral conductor. You would then refer to NEC table 310.16 to determine the conductor size that can safely carry this amount of current, taking into account the conductor's insulation type and the ambient temperature. Additional considerations are: firstly, overcurrent protection. The neutral conductor size must be adequate for the overcurrent protection device, such as a circuit breaker or fuse, that protects the dryer circuits. The ampacity of the neutral conductor must be equal to or greater than the rating of the overcurrent protection device. Secondly, conductor insulation and color coding. The neutral conductor must be insulated and identified by a white or gray color. This is a standard safety practice to distinguish the neutral conductor from the hot conductors. Thirdly, local codes and regulations. Always comply with the latest edition of the NEC and any additional local codes or regulations that may be in effect. Local jurisdictions may have amendments or requirements that supersede the NEC. Fourthly, voltage drop. While not directly related to the neutral calculation, voltage drop should be considered to ensure that the dryers receive adequate voltage for proper operation. Excessive voltage drop can lead to performance issues and premature equipment failure. Voltage drop calculations should be performed for both the branch circuits and the feeder conductors. Fifthly, future expansion. If there is a possibility of adding more dryers in the future, it's prudent to oversize the neutral conductor to accommodate the potential increased load. This can save money and labor in the long run by avoiding the need to replace the conductor later. Sixthly, qualified electrician. These calculations and the selection of electrical equipment should be performed by a qualified and licensed electrician who is familiar with the NEC and local codes. Working with electricity can be dangerous, and it's essential to have the expertise of a professional to ensure safety and compliance. Seventhly, documentation. Keep a record of all calculations, wire sizes, and overcurrent protection device ratings for future reference and inspection purposes. This documentation can be valuable for troubleshooting and maintenance. Eighthly, grounding. Ensure that the grounding system is properly installed and connected to the neutral conductor at the service entrance. This is a critical safety measure that helps to prevent electrical shock hazards. Ninthly, load diversity. The demand factors in Table 220.54 are based on typical load diversity. If the actual usage patterns of the dryers are significantly different, it may be necessary to adjust the calculations accordingly. For example, if the dryers are used more frequently or for longer periods, the demand factor may need to be increased. Tenthly, continuous load. Determine whether the dryer load is considered a continuous load. According to the NEC, a continuous load is one that operates for 3 hours or more. If the dryer load is continuous, the overcurrent protection device and conductor ampacity must be increased by 25%. In summary, calculating the neutral conductor size for electric dryers in apartment complexes requires careful consideration of the NEC, specifically sections 220.54 and 220.61b. By applying the appropriate demand factors and following the steps outlined above, you can ensure that the neutral conductor is properly sized for safety and efficiency. Remember to always consult with a qualified electrician and comply with all applicable codes and regulations. Now let's talk about some specific scenarios and variations that you might encounter when performing these calculations. Firstly, different dryer ratings. While we used a 5 kilowatt dryer rating in our example, the actual rating may vary. It's crucial to check the nameplate rating of each dryer to ensure accurate calculations. Higher rated dryers will obviously contribute to a higher overall demand load. Secondly, mixed-use occupancies. If the apartment complex has mixed-use occupancies, such as commercial spaces in addition to residential units, the electrical service calculation becomes more complex. The demand factors for the commercial spaces will be different from those for the residential units, and a separate calculation will need to be performed for each type of occupancy. Thirdly, shared neutral conductors. In some older apartment complexes, it's possible that multiple dryers share a single neutral conductor. This is generally not permitted in modern installations, but it's important to identify if it exists. If shared neutral conductors are present, the calculations become more complex and require careful analysis to ensure that the neutral conductor is adequately sized for the combined load. Fourthly, energy-efficient dryers. Modern energy-efficient dryers may have lower power consumption than older models. If energy-efficient dryers are used, the rated load per dryer in the calculation may be reduced, resulting in a lower overall demand load. However, it's important to verify the actual power consumption of the dryers to ensure accurate calculations. Fifthly, electric vehicle charging. The increasing popularity of electric vehicles, EVs, is adding new loads to apartment complex electrical systems. If EV charging stations are installed, the additional load must be considered in the service calculation. EV charging loads can be significant, and they may require upgrading the service and feeder conductors. Sixthly, renewable energy sources. If the apartment complex has renewable energy sources, such as solar panels, the service calculation may be affected. The renewable energy source may offset some of the load from the electric dryers, but the calculations can be complex and require careful analysis to ensure proper coordination between the renewable energy source and the utility grid. Seventhly, emergency generators. If the apartment complex has an emergency generator, the generator must be sized to carry the essential loads, including the electric dryers if they are considered essential. The generator sizing calculation must take into account the demand factors for the dryers and other essential loads. Eighthly, load management systems. Load management systems can be used to reduce the peak demand on the electrical system by shedding loads during periods of high demand. If a load management system is installed, the service calculation may be affected, as the system can reduce the demand from the electric dryers and other loads. Ninthly, power factor correction. Power factor correction can improve the efficiency of the electrical system by reducing the amount of reactive power. If power factor correction is installed, the service calculation may be affected, as the amount of apparent power will be reduced. Tenthly, harmonics. Harmonics are distortions in the electrical waveform that can be caused by nonlinear loads such as electronic devices. Harmonics can increase the current flowing in the neutral conductor and can cause overheating. If harmonics are present, the neutral conductor may need to be oversized to accommodate the increased current. 11thly, aluminum conductors. If aluminum conductors are used, the ampacity of the conductors must be derated compared to copper conductors. This is because aluminum has a lower conductivity than copper. The derating factor depends on the type of aluminum conductor and the installation conditions. 12thly, conduit fill. The number of conductors that can be installed in a conduit is limited by the conduit fill requirements in the NEC. The conduit fill requirements depend on the type of conduit, the size of the conductors, and the number of conductors. 13thly, directing factors. Directing factors must be applied to the ampacity of conductors if they are installed in certain conditions, such as in direct sunlight or in close proximity to other heat-generating equipment. The directing factors depend on the installation conditions and the type of conductor insulation. 14thly, ambient temperature. The ambient temperature can affect the ampacity of conductors. If the ambient temperature is high, the ampacity of the conductors must be derated. The derating factor depends on the ambient temperature and the type of conductor insulation. 15thly, voltage drop calculations. Voltage drop calculations should be performed to ensure that the voltage at the dryers is within acceptable limits. Excessive voltage drop can cause the dryers to operate inefficiently and can shorten their lifespan. 16thly, short circuit current calculations. Short circuit current calculations should be performed to ensure that the overcurrent protection devices are properly sized to protect the electrical system from short circuits. The short circuit current depends on the impedance of the electrical system and the available fault current from the utility grid. 17thly, arc flash hazard analysis. An arc flash hazard analysis should be performed to determine the potential arc flash hazards in the electrical system. The arc flash hazard analysis should identify the potential arc flash incident energy levels and the required personal protective equipment (PPE) for electricians working on the electrical system. 18thly, coordination study. A coordination study should be performed to ensure that the overcurrent protection devices are properly coordinated to minimize the extent of an outage in the event of a fault. The coordination study should identify the proper time current curves for the overcurrent protection devices to ensure that the upstream devices do not trip before the downstream devices. 19thly, labeling. The electrical system should be properly labeled to identify the circuits, overcurrent protection devices, and other components. Labeling helps to ensure that electricians can safely and efficiently work on the electrical system. 20thly, maintenance. The electrical system should be regularly maintained to ensure that it is operating safely and efficiently. Maintenance should include inspecting the conductors, overcurrent protection devices, and other components, and cleaning and tightening connections as needed. 21stly, record keeping. Accurate records should be kept of all electrical work performed on the system, including the date of the work, the name of the electrician who performed the work, and the details of the work performed. Record keeping helps to ensure that the electrical system is properly maintained and that any problems can be quickly identified and resolved. These additional points provide a more comprehensive understanding of the factors that can influence neutral conductor calculations in the overall design and maintenance of electrical systems in apartment complexes. Always consult with qualified professionals and adhere to the latest edition of the NEC and local codes.